All right, 1-4, classifying matter. Last section of the first unit. We took a look at matter and we divided it into different sections, but we know that all matter is made up of atoms. So atoms are the smallest part of an element that still has those same properties. Differentiate between element, compound, mixture. Elements, and let's actually look at this flow chart as we answer this. Elements are on the periodic table. We can't break them down anymore. It's like an individual type of Lego. I might have lots of them, but they're all exactly the same. So it's in its own box on the periodic table. It's the simplest form of matter, and it can't be broken down anymore. So these are your elements. Compound, we can take elements, we can take Legos and put them together in a unique way. We can combine them, snap them together, use specific ones, and we always get the same thing. It always has the same formula, it always has the same structure. So there's your compound. Now, elements and compounds are what we call pure. These things always have the same composition. They're pure substances. Mixtures, however, are the opposite of pure. Mixtures, their composition may change. It's randomly thrown together. It's a physical blend, meaning they're not chemically linked. If I look at Na and Cl, there's actually an ionic bond holding them together. If I'm looking at salt and water, I have NaCls and then I have H2Os. Yeah, they're in the same container, but the water isn't connected to the salt. Very simplified version. There's a lot more to this, but that's what you should be thinking in terms of mixture. They're all in there together, and sometimes the particles are so similar in size that we call it a solution. We can't see the differences. But if I put in, I don't know, like dirt and water, dirt is pretty big, water's pretty small, so then I could visibly see the dirt and know that it's different than the water. So this wouldn't really be a solution because the dirt doesn't dissolve. But if the two particles are very close in size, then they dissolve, and we call that a solution. Anyways, random combination, more than one substance, not chemically bonded. They can easily be separated if you use the right technique. So we have to figure out, how can I get these things apart? If it's dirt, it's bigger, I can filter it out. The little water goes through, but the big dirt particles stay up. If it's NaCl, I can't filter that because the particles are the same size. They all go through the same filter together. So I have to think of a new way to separate them. So I have to think of another physical property. And we'll get back to that in a second. Now, decide how each of the formulas below should be classified. We're going to write atom of an element, molecule of an element. So these two are elements, and this is a compound. Now, compound is different elements combined. So let's bang these out right away. Right here I see carbon and oxygen, so that's a compound. That's C. Just C, just Mg, just N, none of those are compounds. Over here I've got carbon, hydrogen, and oxygen. That's a compound, different elements chemically combined. H2O, that's a compound. S8, I only have S, so it's not a compound. NaCl, that's a compound, two different elements. Now, I have atoms of elements. This structure is not an atom. It's 8 atoms bonded together to make a molecule. So that's not just an atom. This is 2 atoms bonded together. That's not an atom. This, since there's just one, that's an atom of the element magnesium. This is an atom of the element carbon. These two are molecules of an element. This is a molecule. It's an N bonded to an N. They're bonded together, but it's the same element. So it's B, a molecule of an element. Over here, I don't want to draw 8 of them, but if you could picture 8 sulfurs, I guess I am drawing a picture, but if you could picture 8 sulfurs all bonded together, that's B, a molecule of an element. All right, back to how to separate mixtures. Remember, it depends on physical properties. Filtration, when we separate things based on filtration, it's based on differences in size. Large particles get caught on the filter, smaller particles pass through. If we're using distillation, we're basing the separation techniques on differences in boiling points. Substances with the low boiling points boil first, they turn into a gas, and then remember we did this with cherry Coke. So here's a cherry Coke mixture. We boiled it. The first particles that went up, they passed through the big tube. Actually, carbon dioxide came out first, and that didn't condense because we couldn't get it cold enough. But after the carbon dioxide was gone, then we took out some of the flavoring, and we sent it around the room, and you all got to smell the cherry Coke. That's because those flavor particles, the molecules that make up that, they rose, they moved through the condenser tube, they finally condensed into liquid, and then they fell into our collection flask or beaker, or whatever we used. And then that's what you smelled. So that boiled at a lower temperature than the water that came out eventually. Once all that flavoring came out, then the temp went up to 100 degrees, and now water started pouring through. Just plain pure water. So differences in boiling points. The ones with lower boiling points come out first. The ones with higher boiling points come out last. Difference between a solute and this should say no, I guess it's right, solvent. My bad. So solute and solvent. Solute makes up a smaller percentage. Solvent is a greater percentage. Now, when we're talking about a solution, this is usually the liquid, and this is the solid. But not all solutions are a solid dissolved in a liquid. Sometimes it might be two liquids. Like what if I gave you a solution of alcohol and water? And then I say which is which. Well, there are two liquids, so you have to know which one's a greater percentage. If this makes up 75 milliliters and this is only 25 milliliters, then you say this is greater, so this is my solvent and this is my solute. And in this case, the water is dissolved in the alcohol because the water is a smaller percentage. Air. Air is a good example of a solution that's not a liquid. Air is about 78% nitrogen and only about 21% oxygen. So air has a solvent of nitrogen and a solute of oxygen, among other things. Brass. Brass is an example of a solution that's not a liquid. Copper makes up the greater percentage, so that's a solvent, and zinc is usually mixed in there, so that's a solute. I'm not going to go over differences in solids, liquids, and gases, but what you should know is it's all about energy. You can get from one state to another by changing the energy. Just skim through this, hit pause, and read through all these. And also know that fixed means same. It's not going to change. So the shape and the volume are not going to change. All right, so let's take a look at a little bit of math here. So we've got a coefficient and we've got a subscript. Coefficient tells us how many molecules there are. It doesn't matter what this formula is. If we see a 10 here, we know we have 10 molecules. If we see a 3, we have 3 molecules. Now this, if we ignore it, let's pretend the 10 is here. If the question says how many atoms are in one molecule, you ignore the coefficient. Let's pretend it's not even there. Now in this case, it isn't there. But if it was there and the question says how much is in one molecule, you ignore a coefficient. This is when you pay attention to the subscripts. The subscripts tells you what's in one molecule. So we see a 2 next to the H, that means there's 2 atoms of hydrogen. We see the imaginary 1, actually we don't see a 1 at all, but we assume it's there, and that tells us there's 1 atom of oxygen in 1 molecule of water. Now over here, we don't see a number after the calcium. That means there's 1 atom of calcium, so it looks like this, Ca. Now we see parentheses. The parentheses tell us this stuff inside is kind of glued together. This is a little package deal. So we have a 2 after the parentheses, so that 2 goes to whatever's inside the parentheses. So here's what I like to do. If you see a 2 there, you know whatever's in the parentheses is going to be written twice. So do that. On the side of your paper, write it twice. And then just count. How many N's do you have? 2. How many oxygens are there? 3 and 3. 6. That's it. Now, if you're really good at this, you don't have to draw it out. You could just say that that 2 gets distributed. Maybe use that word in math class. 2 times the 1 after the N. 2 times 1 is 2. 2 times 3 is 6. So if you're struggling or if you're not quite sure, do I add that? Do I multiply? What do I do? Just rewrite it. Say there's 2 of them, so let me write 2 of them, and then add them up. Now, if we have to figure out the actual mass of the following compounds, you need your periodic table. So the first thing you should do is look at your equation, or look at your formula, and figure out who's involved here, and how many. Well, we have 1 carbon, because there's an imaginary 1 there, and we have 4 hydrogens. Then you have to look at the periodic table. You got to multiply the atomic mass from the periodic table times the number of atoms. So we look on the periodic table for carbon, and the mass is 12.0. And we know there's only 1 in the formula. So 12.0 times 1 is still 12.0. And hydrogen's the simplest element out there, smallest, so it's 1.0. And there's 4 of them. So put a 4 there. What's 1.0 times 4? 4.0. Then you add them together, and that'll get you the grand total. So 12 plus 4 is 16, so we write it over here. And remember, we put AMU there if we're talking about one atom or one molecule. However, if we're talking about a whole mole of them, then we put 16.0 grams, and that's the mass of a whole bunch of atoms or a whole bunch of molecules. That's equal to the mass of 1 mole, or the molar mass. All right, let's do potassium sulfate here. Potassium, there's 2 of them, because there's a little 2 after it. Sulfur, there's nothing there, so it's a 1. Oxygen, there's a 4, so I put a 4 there. Now I've got to take out my periodic table. Look at the molar mass of potassium, K, 39.1 times 2, and we get, what, 78.2? Sulfur, look it up, element 16, 32.1. And there's only 1 of them. There's no numbers after it, so it's 32.1. And finally, oxygen, there's its mass is 16, and there's 4 of them. So 16 times 4 is 64. And then what do? You add them all up, get the grand total. So 2 plus 1 is 3, 8 plus 2 is 10, 14, carry the 1, 7, 8, 8, 9, 10, 11, plus 16, 174. So 174.3, again, if we're talking about one molecule of this stuff, then we say AMUs. If it's asking us how much is 1 mole of this stuff, then we say grams, because that's 1 mole. Okay? Either way, 174.3.